Hello everyone. Hope you are doing well. Welcome to the online platform Civil Techno Breaks. Guys, here we will tune for instantaneous decoding of conceptual knowledge in the field of civil engineering, where study elaborates decoding the earth to build a better world. Today we will learn the core concepts of preliminary geological investigation of dams and foundation requirements in the view of civil engineering. Guys, the structural geology which helps the engineers to understand the geometry, orientation, and formation of rock masses at dam sites. So, the rock mechanics is the study of physical properties of rocks and their significance in engineering projects. Geological investigation identifies the structural components like folds, faults, joints, fractures, and bedding planes affecting foundation stability. So there are so many challenges like lab simulations cannot perfectly replicate the complex variables of natural field conditions. So the laboratory tests provide us the useful data, but actual field conditions are more complex due to the groundwater, weathering, and in situ stresses. So proper geological interpretation is most important and essential for selecting safe dam site, dam alignment, site selection, and preventing foundation failures. With reference to the type of dam, the engineering classification is based on these four parts. So different dam types are selected based on geological and topographical conditions of the surface. Gravity dams require hard, massive, and impermeable rock foundations to resist heavy loads. Arc dams are suitable in narrow valley with very strong abutment capable of resisting arch thrust. Earthen dams are preferred where wide valleys and relatively weaker foundations are present. At the end, buttress dams reduce concrete quantity but require stable and uniform foundation conditions. So, with reference to the geological phenomenon or characteristics of availability of site selection, the classification of dam varies in the four characteristics. As we discuss landscape, just we have to see the investigation methodologies for the same. Surface investigations includes that geological mapping, aerial photogrammetry, remote sensing techniques, and many more. So the investigations are on the surface or below to the surface. So owing towards the subsurface investigations, which involves drilling, borehole logging, trenching, and geophysical surveys. The geophysical methods required or consider the gravity, seismic activity, and magnetic considerations. So core drilling helps determine rock quality designation. Just we can say that RQD, rock quality designation, RQD. So core drilling helps us the RQD, fracture conditions, and groundwater presence. Geophysical methods identify the weaker zones of the rocks, present of the cavities, subsurface discontinuities without extensive excavation. So comprehensive site investigation minimizes uncertainty and improves the dam safety and foundation design. So based on that investigation methodologies, we can prevent the actual landslide or landscape activities. So landscape is nothing but the actual availability of ground surface. That ground surface may be surveyed by the aerial photogrammetry where detecting the large scale structural features observed by vegetation, water, or any type of soil and rock types. Now, by checking the suitability of rock, we have to check the competence and strength for the same. So rock competence refers to the ability of foundation rocks to withstand the dam loads without excessive deformation. So foundation must have be strong so that there will not be any deformation or displacement at the existing structure. Compressive strength testing evaluates whether rocks can safely support structural stresses which are acting on it. The strong and dense rocks provide us better stability and lower settlement under the dam loading. So dam loading is not constant phenomenon. Dam loading may change with reference to the vibrations in the earth crust. So weak, weathered or fractured rock may require treatment such as grouting or excavation replacement. Engineering properties of rocks directly influence foundation design, excavation methods and dam stability. So by confining the pressure point of view, rock strength and ductility increase with reference to the depth. So the graphical representation shows that strain in percentage with reference to that stress which is acting. So the increasing strength and ductility and strength. So by ductile property, we can see the graphical representation where 0.1 MPa to 60 MPa. So we have to go for increasing the strength. So the acting load must be checked on the basis of the availability of type of rock, just like basalt, quartzite, limestone, sandstone, shale, marslot, robotic slab. So with reference to that rock types, we have to check the competence of that rock, strength of that rock, where the suitability of rock is identified, and we can finalize the existing dam like structure or site suitable structure. Now structural defects. So we have to construct any type of structure just like dam on the surface. So site selection criteria plays an important role. Before that, we have to go for the geometry of weaknesses just like defects. So what are the defects in the earth crust with reference to the bedding planes, with reference to the tectonic plates, with reference to the classification of deformation, with reference to the uh, fold, fault, planes, everything. So first image, which where horizontal beds are there, they provide stable support where risk is leakage along bedding planes only. So rock strata is there, dam location and reservoir. At the second, upstream deep, where upstream deep shows that a more stable thing. Why? Because the tectonic plates are in upward direction with reference to the dam wall. So water pressure closes joints, and here high friction will be noted. At the third point or third defect, downstream deep. Downstream deep, which is a critical danger. If the ground surface or ground subsurface noted that the downstream deep, then the component of weight acts with water pressure where high risk of gravity sliding will be there. So dam overturning effect will come in picture. So this is the actual structural defect or geometry of weakness with reference to the tectonic plates. So geological structures such as horizontal, inclined and folded beds affect the dam foundation behavior. So upstream or downstream dipping strata may create sliding planes and seepage paths. So orientation of discontinuities relative to the dam axis is critical for structural stability analysis. Detailed structural mapping, which helps engineers to identify the potential failure mechanism before construction starts. Second type of defect is related to the faults and shear zone. So fault scrap and the triangular facets. So where definition for that is planes of displacement often associated with crushed rock zones. So basically fault planes divide the existing tectonic plates, or we can say that shuffle the tectonic plates in upward and downward direction. So due to that, the major hazards will come in picture with reference to the shear zones. So faults and shear zones are weak geological regions that reduce foundation stability, where the active or major faults near dam sites can create serious seismic and structural hazards. These seismic hazards may result in the overturning of dam or the leakages from the dam. Sheared rock masses generally have low strength and high permeability. Due to that, geological investigations which determine fault activity, displacement history and the groundwater movement below to the earth surface. With reference to the weak fault zones, require excavation, grouting, or relocation of dam alignment as a preventive measures, or we can say that mitigation techniques. So field detection is based on the triangulator facets on mountain fronts, offset streams and ridges, springs align along foot of slopes. And the hazards are the gauge zones, breccia, just like rock types, and reactivation. Reactivation is the potential for displacement during seismic events. When earthquake occurs, then displacement will be there. So we can say that reactivation. Breccia, where crushed rocks reduces bearing capacity. So we want hard surface rocks and continue rocks. There will not be any cracks or crush activity. Third type of structural defects are related to the joints and faults. These joints are of two types, and anticline and syncline. Okay, anticline are in upward direction, syncline are in downward direction. So tension cracks at crest portion where high leakages will occur, and artesian pressure trap in the syncline. So even massive rock is fractured. These are the arteries for water escape, just like the percolation or seepage activity. Through that cracks, water will enter and the whole tectonic plates may get disturbed. So the joints are natural cracks in rocks that influence permeability and rock strength. Closely spaced joints reduce rock mass competence and increase seepage risk. Fold structures like anticlines and synclines affect groundwater movement beneath the dams. Engineering treatment includes rock bolting, grouting, and drainage control systems to avoid such type of defects. Is that the enemy for the dam where permeability and seepage? See the diagram where the actual dam wall will be based on that various tectonic plates below to that, where uplift pressure is acting from downward to upward direction. The whole water is stored in the upstream side. The whole weight of that water is acting on the wall of the dam. So with reference to that percolation activity, the amount which is stored of water in the reservoir gets percolated through the seepage, and if that seepage flow, just like shown in the blue line, with reference to the flow nets or seepage paths, then there will be a huge disaster for that dam site. So the seepage through dam foundations can lead to uplift pressure and piping failure. This is also called as a piping failure. Uplift pressure or piping failure. Permeable rocks allow water flow through fractures, joints, and porous zones. Excessive uplift pressure reduces effective stress and weakens foundation stability. So drainage galleries, grout curtains, and cutoff walls are used to control such type of uplift pressure, or we can say that piping failure. Proper seepage analysis is essential to ensure the long-term dam safety and performance. So as pore pressure increases, the effective confining pressure decreases. As pore pressure increases, effective confining pressure decreases. So if x is equal to 1, friction approaches. If x is equal to 0, sliding failure will occur. The engineering intervention, or we can say that the technique which is used to prevent such piping failure or such type of sewage analysis, we have to go for grouting and rock curtains. So what is the objective behind that? Artificially restore rock competency and massiveness. Grout curtains, we are providing artificially or just like the man-made activity into the ground surface, which where we can provide impermeable barriers. We can provide impermeable barriers. So grouting improves the strength and impermeability of foundation rock. Consolidation grouting fills shallow cracks, joints, and weathered zones near foundation. Curtain grouting creates deep impermeable barriers to reduce water seepage beneath the dam. Grout curtains help minimize uplift pressure and increase the overall stability. Foundation treatment measures significantly which improves the safety and service life of dam. So consolidation grouting, curtain grouting, these are the two methodologies we can prefer, just like the intervention in the natural tectonic plates to improve the stability of the dam. The stability of reservoir slopes, where the gravity pull concept is there. The reservoir slopes may become unstable due to water saturation and reduction in shear strength. Due to the water saturation and reduction in the shear strength. So landslides into reservoirs can generate impulse wave capable of overtopping dams. So landslides are the huge hazards. Rapid down, rapid drawdown conditions reduce slope stability because water pressure supports decrease suddenly. So there will be a high risk of landslides into the reservoir which can generate impulsively waves, just like we can say that tsunamis, which causing the dam overtopping. Geological investigations assess slope, angle, rock discontinuities, forms of rock characteristics, weathering conditions. So stabilization methods includes drainage systems, retaining structures and slope reinforcement so that we can stable the reservoir slopes. Triggering the earth, where reservoir induced seismicity concept. So RIS, reservoir induced seismicity. So what is the mechanism behind that? Three parts are there: load, lubrication, failure. Load, lubrication, failure. So the graphical representation where time, which is in the relative units on the x-axis, whereas reservoir water level, which is in meters. So the graphical representation shows that the initial filling near to the zero, then after that reservoir water level, and at the end seismic frequency, where number of events are marked with reference to that lag time which is shown. The actual initial filling goes on increasing moderately, but at a time it increases suddenly, where the water level of the reservoir is at the top. So with reference to that reservoir induced seismicity, we have to check the load, lubrication and failure. The mechanism load consists of the massive weight of water adds stress to crust or to on the wall surface, at the same time to the beds of the rock or bed of the dam. Secondly, lubrication, where water penetrates deeply through the plot, through the faults or the fractures which are available below to that foundation. And the failure, which is the result where pore pressure reduces effective friction, triggering movement on dormant faults. So the triggering the earth based on the reservoir induced seismicity occurs when water storage triggers movement along existing faults. Massive water load increases stress on the earth's crust near the reservoir area. So water infiltration into deep fractures increases pore pressure and reduces fault friction. So reservoir induced seismicity generate earthquakes affecting dam safety and surrounding infrastructure. Continuous seismic monitoring is most important and essential point for the dam during reservoir filling and operation stages, just like during the rainy season and after the rainy season also. Here the case study is discussed of most popular Koyna dam from India. The Koyna dam is one of the most important example of reservoir induced seismicity in India. Geological conditions and deep fault systems contributed to earthquake activity after reservoir filling. In 1967, Koyna earthquake highlighted the importance of seismic investigations in dam projects. Engineers improved the monitoring systems, instrumentation and structural safety measures after that 1967 earthquake event. The case emphasizes that the need for detailed geological and seismic assessment before dam construction. So the analysis is based on the basalt is a strong rock which sustain the heavy load, high breaking strength, but columnar joints allowed deep water penetration from the same. So the result is that elevated pore pressure lubricated a shear zone underlying the traps where the water is flowing through that cracks, and due to that crack flowing water or the piping event or the seepage, there may be a problem for the dam safety. So even stable shield areas can react to massive engineering loads. Means If basalt is a strong rock is available beneath to that Deccan trap where Koyna Dam is situated or located, huge massive basalt flows is there with reference to the tectonic plates. Due to that also, in 1967 earthquake will occur, but the dam is but the dam is at the same location without any disruption with reference to the tectonic plates. Why dam fail? So why dam fail means just like the disaster. How the disaster will occur with reference to the dam point of view, just like to the foundation failure. So dam failures commonly occur due to the foundation defects, seepage, slope instability, and poor geological assessment. Weak foundation can cause settlement, sliding, or structural cracking in dams. So 30% due to the hydrological overtopping, 30% due to the structural impact, piping impact, or 40% due to the geological foundation failure. So main takeaway is that 30 to 40% of all dam failures are attributed to inadequate geological investigations, just like the availability of tectonic plates, hard rock, stability, everything. So foundation failures are sliding, piping, and uplift. Sliding is due to the faults or clay seams. Piping is due to the internal erosion through joints, and uplift is the uncontrolled pore pressure. So at the end, geological investigation is a critical component of dam planning and foundation engineering. Understanding the rock mechanics, structural defects, seepage, and seismicity ensures safer dam construction and life. Modern investigation techniques improves reliability, safety, and long-term sustainability of hydraulic structures. Civil engineers must integrate geological knowledge with structural and hydrological design principles for successful dam projects. Stay tuned, guys. Happy learning.